welcome back to ICP. Today we're going to talk about wave characteristics. All right, first thing we're going to talk about today is amplitude. Amplitude is the distance from the rest position. So here's our rest position. This right here is amplitude. This is amplitude. The amplitude is the distance from the rest position to a crest or a trough. Again, from the rest position to a trough, rest position to a crest. We measure it in meters. The next thing we'll talk about then here is wavelength. Wavelength on a transverse wave, which is the top one, can be measured from crest to crest, from here to here, or from trough to trough. On a longitudinal wave, it can be measured from rarefaction to rarefaction or compression to compression. Those are all wavelengths. Again, we measure it in meters. One of the things that's hard for students to remember, a little key thing here, is the symbol is this phi. All right. Well, what do amplitude and wavelength tell us about energy? Because everything's about energy here in ICP. And what we find out is larger amplitude, all right, means more energy. Shorter wavelength means more energy. So again, larger amplitude, more energy, shorter wavelength, more energy. So the higher a wave is, the more energy. And the more waves we have, more energy. Okay, another thing we're going to talk about here is period. Period is just simply a time for one cycle to happen. This person over here on this wave is going to go down and back up. And that's what you see here. Now they're about halfway down, and now they're back up. Well, how long did it take then to get from, we're going to call this wave A to wave B? You see, here's wave A, here's wave B, and now we just have wave B, and wave C is starting to come. How long did it take to get from top of wave A to the top of wave B? It took 2 seconds. Notice that our units, all right, our units are seconds. Our symbol is a capital T, and this all stands for period. Okay, frequency. Frequency is the number of cycles or vibrations per unit of time. Our symbol here is an F for frequency. We use a lowercase f. The units are hertz, and this is all going to be hard because this is all words and lingo that you guys don't use every day. In the diagram here, we find the frequency is 0.5 hertz. I don't really like this, but really what this means is how many times does he go up and down per second? All right, and forget about this bottom part here. He's only gone down, he's only made 1/2 of a cycle because he's only gone down, if you notice here. He's down to the bottom. He's at the trough. He was at the crest, and he's at the trough. So he's made half of a cycle, half of a complete revolution in a second. So his frequency then is 0.5 hertz. If he'd gone down and back 3 times in a second, say there's a lot more waves, then his frequency would be 3 hertz, and so forth. Let's put everything together then. Amplitude, which we learned about already, was the distance from rest position to crest, or from rest position to trough. Wavelength is the distance, in this case we could say from crest to crest, or you could also do it from trough to trough, and again we're going to use our phi for wavelength. In the frequency, how many waves are going to happen in 1 second? Well, they've said that there are 5 waves that have come by in a second. So that means 1, 2, 3, 4, 5, approximately 5 waves. It's moving pretty quickly. Okay, frequency is the inverse of period. And basically, so here's some of our first math that's coming into us here. Frequency is 1 over the period, or frequency is 1 over the capital T, and then period is 1 over F. So some examples of that would be if we knew that the frequency, let's say, was 3 hertz, then we could find the period. The period would be 1 over 3 because it's 1 over F. So that would be 0.33 seconds. And likewise, if we knew, let's say the time was, I don't know, let's just make one up, 30 seconds, there we go, then we can know the frequency is 1 over 30, which is going to be a really small number. Right? The larger the period, the smaller the frequency. Likewise, the larger the frequency, the smaller the period. They are inverses of each other. Okay, some more math here for today. Wave speed equals wavelength divided by period. So what we have here then is the wave speed, that's going to be represented by V, equals the wavelength. Well, for lax, I don't really have a lot of those phi's, I use L in here for wavelength, and period then obviously is the T. In this case, wave speed, frequency, wavelength. Let's take a look at some examples here. The string of a piano that produces the note middle C vibrates with a frequency of 262 hertz. That's going to be important, I guarantee it. If the sound wave produced by this string has a wavelength in air of 1.3 meters. So it says, what is the period of the wave? Well, period is how long does it take for one vibration to have. Period equals 1 over F. In this case, the frequency is 262, so it's 1 over 262. So the period is equal to 0.004 seconds. What is the speed of the sound waves? Well, I'm going to use my velocity equals frequency times wavelength, right? And because that's the speed, and that's going to be, the frequency is 262 hertz times the wavelength of 1.3. The velocity in this case turns out to be 340.6 meters per second. Now, here's the problem I want you to do on your own. I am going to give you a hint again. The period is 1 over the frequency. And again, in this case, they want you to find the wavelength. They want you to find the wavelength. You're going to use V equals the frequency times the wavelength. You're going to be solving for L. Okay, the speed of a wave depends upon the medium. What this means then is in different materials, sound or waves are going to travel at different speeds. They'll travel different in water than what they do in air. These are all obviously for mechanical waves. Electromagnetic has one speed because the medium doesn't matter for the most part. But what we find out is that wave speeds are greatest in solids, and that's because the particles are very close to each other. When they make collisions, the energy can travel very quickly. Wave speed is least in gases, and that's because they're very far from each other. They've got to travel, hit this one's got to come over here, hit this one, for that chain reaction to happen. In a given medium, the speed of a wave is constant. So the speed of sound in water is always going to be the same. The speed of sound in air is always going to be the same. And again, this right here is for mechanical waves. Down here at the bottom, basically we're talking about electromagnetic waves. Light has a finite speed. It's never going to change for the most part. I mean, when we say never, we mean it's not really going to change very much whatsoever at all. But a lot of times we just simply use a given here, 3 times 10 to the 8th meters per second. And that's the speed of light. Well, hey, I know this was a little bit longer today. Hopefully you enjoyed it, though. I'll catch you on the flip side.